Hello, chemists. This is Ms. Placino, and you are watching lesson 1.3 on measurements and density. In today's lesson, we're going to focus on how to properly make measurements and then how to evaluate those measurements. And as you may have guessed, we're going to tie it back into density. So we've got 4 goals for today's lesson. First, we're going to learn how to record measurements to the proper number of digits. This is a skill that will really serve you well in the lab. Next, we're going to be able to identify the uncertain digit in a measurement and explain why it is uncertain. We're going to apply the density formula to solve problems. There's a good chance you've already been introduced to this formula. And we're going to apply the percent error formula to solve problems as well. All right, let's get into the lesson. So let's first start by talking about density. If you had to explain to someone what density is, not just provide a formula, but try to explain what density is, you might get to the idea, well, it's how much matter, how much stuff have we squeezed into a given amount of space. The more stuff in the space, the greater the density is. The less stuff, less matter in that space, the lower the density is. So something like this is showing really high density. We've got tons and tons of atoms packed into this space. The formula for density is mass divided by volume. Most of the time in chemistry, we'll end up using grams per milliliter. We could also see grams per centimeter cubed used frequently. Don't get thrown off by that. 1 milliliter is equal to 1 cubic centimeter. Those are one and the same. But technically, you could use any mass divided by any volume as the units. You could do pounds per gallon. You could do kilograms per liter. Again, usually we'll stick to just those two. Often in the lab, we're measuring fairly small quantities, so there's no need to really go overboard with large units. If you're having trouble kind of conceptualizing density, let's relate it to another class where you might talk about density, maybe in terms of population density. So we teach and go to school in New York City, and let's compare it to a place that you probably haven't been before. I'm guessing most of you have not been to Nebraska. I can't say that I've been there either, but I know what New York City looks like. It is people on top of people on top of more people. It is super, super crowded in a really high population density. I think we've got the highest population density in the country, about lots of people per square mile. If we compare that to what I imagine Nebraska looks like, I think it's just this one guy. Like, there are very few people, comparatively speaking, per square mile. So New York City, very high population density, a lot of matter per space. Nebraska, a low population density, very few people per square mile usually is the unit they use, but you could just kind of think of it as little matter per the same amount of volume. So that's just another way to think about density. All right, so if we were in class, we'd be doing this demonstration. We'll kind of just walk through it virtually now. What will happen if a can of Coke and Diet Coke are placed into a large container of water? I'll give you a hint, it won't explode, nothing crazy like that. Take a second, pause the video, and see if you can kind of brainstorm what you think might happen. Okay, hopefully you've done a little bit of brainstorming. If I take those 2 cans of soda and I place them into that beaker of water, ultimately what I should see is this. I end up with the can of Coke sinking to the bottom of that beaker of water, and then the can of Diet Coke floating just a hair above the water level. Why do you think this occurs? A rookie mistake is to say something to the effect of, oh, the can of Coke must weigh more than the can of Diet Coke. Well, careful, what topic have we just spent the last 2 slides talking about? Yeah, this is an issue of density. I can say that the can of Coke has a density greater than water, and the can of Diet Coke must have a density less than water. If you think about what's inside these 2 sodas, and we'll start with Coca-Cola. If you ever read the ingredient label or you look at like the nutritional facts, you should know that sugar is packed that soda, excuse me, is packed with sugar, usually on the order of like 30 to 40 grams, depending on what soda you're looking at. Water, then you've got some artificial coloring and flavoring. And if you compare that to something like a diet sodas are mostly water, and then they have artificial sweeteners that are many, many times sweeter than sugar. So you can use trace amounts and kind of get that same sweet flavor. So we can say that the Diet Coke must have a lower density than both Coke and water, and that's why it's floating. If we were in class, we would go through and we would really kind of just check that out. We'd find the density of these two materials and water. So let's go ahead and kind of brainstorm now. Pause the video. Think about if you were in the lab or in the classroom and you wanted to determine the density of Coke, Diet Coke, and water, what would you need to do? And maybe how would you do it? All right. Hopefully you know that there isn't any instrument that is going to measure density directly. I'm going to have to measure two different values. I'm going to do some math to find the density. So I've got measure volume first. I need something like a graduated cylinder so I can measure how much in terms of milliliters soda I'm working with. I need to measure the mass as well. We know density is mass divided by volume. So something like a triple beam balance or an electronic scale will do the job and measure the mass for us. At that point, it's just a math problem. I have my mass, I'll divide it by my volume. That will give me my density in terms of grams per liter. And I would simply repeat that for the other liquids. So, measuring mass is going to be easy, especially if we're using a digital scale. It'll just spit out a number and you can record it. Measuring volume from a graduated cylinder requires a little bit more work, so let's talk about that now. We go to take measurements. If we're using analog equipment, so basically equipment that does not have a digital readout, you've got to use proper measuring techniques. And you may have been introduced to this before in a previous science class. It's not a difficult technique to use, but students forget about it a lot in the lab. So we'll look at some cutaways of graduated cylinders. Now these are three different graduated cylinders. They all do the same job. We use them to measure volumes. But if you look at the tick marks, the lines on the graduated cylinders, you'll see that each of them represent a different value. For example, and I'll just number these to make it a little bit easier to talk about. 1, 2, 3. Each of the lines or the tick marks on graduated cylinder 1 represent 1 milliliter. Graduated cylinder number 2, each line represents 10 milliliters. Graduated cylinder number 3, 2 to 3, 10 of them in there. It's 1/10 of a milliliter. So when we use these different graduated cylinders, we're going to be expressing our measurements to a different number of digits. So really the first thing you want to do when you have a piece of equipment that is analog that you're using to measure is figure out what place each tick mark on the instrument represents. We just did that. When you go to report your measurement, you want to report one place further to the right. Let's look at graduated cylinder number 1 together. All right, so I can pretty confidently say that the water level, or the liquid level, I guess I don't know that this is water, is somewhere between 44 and 45 milliliters. I need to estimate one place further, so I know it to the ones place. I'm going to estimate the tenths place. Since it's an estimation, it is uncertain. The last digit in a measurement is always uncertain. And what I see and what you see might not be the same. It doesn't mean one of us is right and one of us is wrong, so long as we're reporting to the correct place. So when I look at this, I see 44.9 milliliters from the bottom of the meniscus. Maybe you see 44.7 or 44.8. All of those are okay. We know the 44. The last digit is uncertain. Go ahead and try out graduated cylinders 2 and 3. All right, graduated cylinder 2, I know to the tens place, one place further to the right is the ones place. It's about 22 milliliters. In this case, The 2 was uncertain. I had to estimate it or kind of take a guess. Graduated cylinder number 3. I see this as 2.64 milliliters. It's definitely between 2.6 and 2.7. I had to take a guess at the hundreds place, so it is the uncertain digit. And I will be reminding you of this when we're in the lab, and we'll get some more practice in. All right, so I went through, and I'd like you to start to fill out your data table, but I went through and I took some pictures. So in my data table, we know that we need mass and volume. Start with mass. What unit do we use to measure mass? I talked about it earlier. We're going to measure in terms of grams. So my sample of Coke had a mass of 26.66 grams, Diet Coke 41.44, and water was 30.59. Record those into your data table. Volumes. So they're going to be reported in milliliters. We'll give you a little bit more time to practice with measuring. It's harder doing it in the lab and doing it in real life than it is looking at like a drawing. But do the best you can. See if you can figure out or determine how much or what the volume of the soda and water is in each of those graduated cylinders. So pause the video, check them out. All right, when I look at this, and again, the last digit is uncertain, all of these graduated cylinders, each of the tick marks represents 1 milliliter, so I need to estimate one place further to the right. I estimate to the 10th place. To me, this looks like it's 25 right on the nose. So I'm going to say 25.0. And it's a little bit tougher in the Diet Coke. There's a lot of bubbles, making it difficult to see. I think it's just over the 41 milliliter mark. So I'm going to call it 41.1 milliliters. Again, you may agree or disagree with these numbers so long as they are close and they are estimated to the same place. Water, I see this, I don't know, maybe just a little below the 31. So I'm going to call that 30.8 milliliters. Okay, so it's kind of a summary of what we've got. We've taken care of the actual measurements that we need to make, and now we're just down to calculations. So we're going to calculate density and percent error. So let's talk about density first, and really just kind of what I'd like you to do when you go to show your work. I am a stickler for how you show your work. I think it's really important to communicate how you're going to solve the problem and then walk me through it step by step. So we know the 2 calculations we'll end up performing are percent error and density. What needs to be included when showing work? Well, first and foremost, you need to show me a formula. You don't have to write out the whole words in the formula. Abbreviations are fine, but always, always, always start with the formula. So if we're doing density, something like density equals mass over volume, D equals M over V, is perfectly acceptable. This communicates, hey, this is how I'm solving this problem. Next, I want you to substitute. Ooh. So I want you to take your values and plug them in. I would highly recommend substituting with the units. Not so much in chemistry, at least at this level of chemistry, but when you go to take physics, you do a lot of unit derivation, and you got to get units to cancel to come up with new units. Getting into the habit of including the unit with the value is going to make your life a lot easier. So plug in your numbers with units. And finally, answer with units. So make sure that you have your numerical value and the unit. You need both to earn full credit, and if you would be so kind, it's great to have a box around your final answer. It just kind of makes it easier for me to find, and to me that kind of means that you are done with the problem. I think it's from your reading, but just in case, we know that's the density formula. What's our percent error formula? Percent error, we're going to take our measured value, subtract the accepted value, divide by the accepted value, and multiply by 100. The measured value is the value that you've come up with. You've measured these things in the lab. The accepted value, or the actual value, that's the number that the scientific community has agreed on. Sometimes you'll see the percent error formula with those like absolute value bars around it. We do not use them in chemistry. Percent error can be negative, and it can be really helpful to know if you're too high or too low. That usually sends you to some different errors that could have possibly occurred. What I'd like you to do is pause the video, pick one of the three liquids, Coke, Diet Coke, or water, calculate the density, calculate the percent error, and we'll check back in just a minute. All right, so let's go through with Coca-Cola first. Density, mass divided by volume. I came up with 1.006 grams per milliliter. The accepted value is a little bit lower than that, so my percent error is going to be positive. I got about 2.3% error. That's pretty good. Diet Coke, mass divided by volume. Came up with 1.008 grams per milliliter. Again, a little bit on the high side. Small percent error, 1.1%. And finally, we've got water, mass divided by volume, 0.993. So just a little bit lower than the accepted value. So in this case, my percent error will be negative. All right, so hopefully you agree with the math. Maybe depending on how you read the volumes in the graduated cylinder, we might have slightly different numbers, maybe rounded differently, but hopefully you don't have anything that's too far out in left field from this. Okay, just to wrap up, we'll give you some questions to think about. Usually when you're doing like lab work, you want to summarize your results of that experiment. That's really, really easy. Instead of that kind of a table, it might be nice just to rewrite them in the summary box. Do your results contradict your observations? Let's go back to the results real quick. Those seem contradictory. Diet Coke we saw floated in the water, so it should have a lower density. But when we went through and did the calculations, based on our values, we have Diet Coke with a greater density than water. So based on this, we would have expected to see the Diet Coke also sink. That doesn't mean that the water is broken or the soda is broken by any stretch. We probably have some sort of error somewhere. So this definitely does not, our data does not support what we saw with the demonstration. That's okay. That's going to happen from time to time. Do not falsify your data. I'd rather see, your real ugly data than some, made up, very pretty fake data. So yeah, they contradict. We ended up with a density of water less than the density of Diet Coke. And finally, what's one potential source of error in this activity or this lab? We don't say human error. We don't say things like, my lab partner messed it up, or maybe I didn't read it correctly. We also tend not to blame instrumentation. We don't say things like the scale was broken. Well, why would you use a broken scale? I think probably the best source of error in this lab is just difficulty reading the graduated cylinder. There was a lot of carbon dioxide bubbles in the Diet Coke one in particular, and that could have made it harder for us to see. So I think that is a potential error, and if you came up with other ones, great. But I think that's a good one too, and that's a really easy one to see too. All right, sorry this lesson was a little bit long today. Thank you for tuning in, and I hope you found this helpful.